This is part 2 of our polynomial cam design discussion. Here we're going to do a 3, 4, 5 polynomial for a double dwell cam design. Previously we looked at a single dwell design. So for this double dwell cam design we're going to use two polynomials. We're going to use a polynomial for our rise and another polynomial for our fall. Again, we do not need polynomials for the dwell portions. During the dwell, no function is needed because the values simply remain what they were at the beginning of the dwell. The motion requirements for the rise and fall are shown below in this table, where beta 1 and beta 2 are both equal to 90. They're equal in this case, but they do not have to be. And in this particular example, our h is going to be equal to 1 inch. And so we see in our first two rows our rise requirements, or our rise boundary conditions. When theta is equal to 0, our position is equal to 0, our velocity and acceleration are also equal to 0 because we're matching up to a previous dwell. At the end of our rise, where theta is equal to beta 1 or 90 degrees, our s is equal to h or 1 inch, our velocity is equal to 0, and our a is equal to 0 because we're about to dwell. It's important here that we specify that our acceleration is equal to 0. If we did not, even if our velocity was equal to 0, an instant later with a non-zero acceleration, we would have a non-zero velocity. And this should not happen if we're dwelling. And so it's important that we also specify our acceleration. And so we have 1, 2, 3, 4, 5, 6 boundary conditions, meaning that we're going to have a fifth order polynomial for our rise. The fall is similar. Again, a brand new polynomial. Theta equals 0. We'll have s equal to h, v equal to 0, and a equal to 0. So again, we must remember that we have a dwell in between the rise and fall, and this is why our velocity and our acceleration are both set equal to 0 at this point in time. At the end of our fall, where theta is equal to beta 2, which is 90 in this case, s is back down to 0, our velocity is 0, and our acceleration is 0 because we're about to match up to a dwell before we then begin our rise function again. So again, we have 6 boundary conditions for the rise, so we need a polynomial of degree 5. And so here we have our generic position equation with c0 plus c1 times theta over beta all the way up to c5 times theta over beta to the fifth. Again, fifth order polynomial because we have 6 boundary conditions. This is going to be the generic function for our rise, the rise portion of our polynomial. The same function exists for the fall because it is also a fifth order. Now we have our velocity and our accelerations. These come from the first and second derivative of our position equation. We showed a little bit more of how to do this in our first presentation on polynomial cam design, where we were doing a single dwell design. Again, we must remember that we're taking these derivatives with respect to theta, meaning that the units for velocity are inches per radian or inches per degree, and for acceleration, the units would be inches per radian squared or inches per degree squared. Now we need to substitute in the boundary conditions from our table to determine the various constants that we have. So where theta is equal to 0, our s should be 0, and we find that our c0 is 0. The same happens for our velocity and our acceleration, meaning that we found that c0, c1, and c2 are all 0. And so we look back at our equations. We have found c0, c1, and c2 to be 0, but we still need to find c3, c4, and c5. That is done using the second row in our table. For the second row, theta is equal to beta, or beta 1 since we're focused on the rise. In that case, it is 90 degrees. Our s should be equal to h at this point in time, which means that we're going to get c3 plus c4 plus c5 for the rest of that equation. We do the same for velocity and acceleration, and we get the following equations. And so you'll notice that we have 1, 2, 3 equations and 3 unknowns, c3, c4, and c5. Again, we can do this solution by hand, or we can put each equation into matrix form, these 3 equations in the matrix form, and solve, finding that our c3 is equal to 10h, our c4 is equal to negative 15h, and our c5 is equal to 6h, resulting in a rise polynomial as shown here, where position is equal to the following. And of course, we can also get our velocity, our acceleration, and our jerk equations by differentiating this position equation, or simply by plugging in these c values to the equations that we had here for velocity, here for acceleration. And of course, we need one more derivative for our jerk equation. When we plot our result, we get the following for our rise. We see that it's a nice looking curve for the rise, for the velocity, acceleration, and jerk. We are continuous through the first and second derivatives, and the corollary to our fundamental law, our jerk is finite. And so this is a good result for our CAM design. The fall would have a similar looking set of equations. We won't focus on the fall for this particular case. But what we're going to do now is we're going to go and expand a polynomial and do a design that's slightly different. In this case, we're going to do a 4, 5, 6, 7 polynomial CAM design. We previously used a 3, 4, 5 polynomial, which had 6 boundary conditions total from the position, the velocity, and the acceleration. If we add a constraint that our jerk also be 0 at the beginning and end of the rise, we'll get 2 more boundary conditions for a total of 8 boundary conditions. So we look back at our equation, what we're saying is that we like to have a jerk that also starts at 0. This is not required. The jerk here was finite, but if we did want our jerk to begin at 0 and end at 0, that would require 2 more boundary conditions for a total of 8. This would be a 7th degree polynomial, but we use the same solution techniques as we did for the 3, 4, 5 polynomial. We do that, we get our S equation looking as follows: 35, 84, 70, and 20 for our C's. And you see this is a 4, 5, 6, 7 polynomial. The result is very similar to what we had for the 3, 4, 5 polynomial, except our jerk function does indeed start at 0 and end at 0 for that rise function. And so it's a nice jerk function which is piecewise continuous, so a very nice result in terms of this particular CAM design. And that's the end of our second presentation on polynomials for double dwell CAM design.